is a method. So what do you mean by artificial intelligence? Artificial intelligence is the method that refers to a system or a machine that imitates humans' intelligence to perform the functions. So when you talk about artificial intelligence, it was developed way back in 1950 in the computer science sectors, and it copied the human mind to develop machines that can process methods, perform based on the data given to the system. So what I understood when I was going through the literature is that everything depends on the data, and it's all about the big data what we have in terms of the artificial intelligence. AI refers to the simulations of the human intelligence in machines. So how does human think? We all think in terms of our observations. Whatever we have learned through our intelligence is all about observations. So for example, when you type from 1 to 9 and there is a number missing, we all predict based on our observation that it will be number 6 there. So similarly, when in terms of chemistry, when you look at these examples of esterification and take your acids from benzoic acid and start adding the substituted alcohol, you always see that what can be made in terms of ester in presence of the acid. But when it comes to the isopropyl alcohol, the final predictions based on the observation will be that you need isopropyl alcohol to make that particular esters there. So now based on this, how you will engage computers or how you will request computers based on the algorithms on how they can think and predict in terms of the chemistry. You need data. So this kind of data coming out of various literature spaces will help the computer systems program with the algorithms and with the required necessity functions to develop those systems in predictive tools. And I will touch base upon that in the later part of my presentations. So in general, when you talk about the artificial intelligence, machine learning or deep learning, as you can see from the picture on the left-hand side is that everything is actually a subset of artificial intelligence, be it machine learning, be it the deep learning, or be it the explainable AI. When you talk about explainable AI, that is the innermost part of this model, which is used to provide the explanation of the methods, the procedures, or the output of the overall processes there. When you talk about machine learning, it is a technique that allows the computer to identify various patterns, make predictions which are more accurate or closer to the accuracy, and which can be refined again based on the data, based on the experience, based on the precisely programming what we can provide to the machine learning. When you talk about the overall process of the machine learning, the artificial intelligence algorithm provides you to decide or make the decisions in terms of everything what you feed into the systems. One can integrate the artificial intelligence in the systems to help it perform faster the task what you want to achieve, or in terms of the execution, you can improve your efficiency of predictions there. It also helps you to predict decisions and solve complex problems. So everything starts from the data. We have to gather the data, prepare the data, and ultimately train the model. The more you train the model, the more you feed the data into the systems, the better the predictions of the machine learning systems will have. So when you talk about machine learning in general, I have captured 4 basic points of what machine learning can be doing in terms of the artificial intelligence machine learning systems when you talk about feeding the data in terms of chemical sciences into the computers. So it can achieve either as a deep learning part, whereas when you talk about deep learning, it is learning from the data through the layers of iterations there. You keep on iterating the data, the kind of data you feed into it. Then you try to optimize the unstructured data and the big data. One can also do the reinforcement learning in the machine learning system, either with the behavioral learning model or try and error learning processes there. One can use unsupervised learning, which is completely unlabeled data. So it is all scattered everywhere, and then try to organize that unlabeled data, which can be substituted as unsupervised learning there. When you talk about supervised learning in terms of machine learning, whatever the data you have gathered, one has gathered, is all classified data, and it helps to speed up the process or to nullify the process of iterations faster when you talk about in terms of machine learnings. Switching now gears to the kind of information is available in terms of literature space when you talk about chemical sciences and what artificial intelligence and machine learnings have to offer in terms of the publications in chemical sciences. If you refer to this picture, you clearly see that lot of developments or lot of research has been happening in terms of analytical chemistry or biochemistry when compared to inorganic chemistry or organic chemistry, which are at the bottom half of this picture there. And major developments have started after 2015, and there is a real spike in the development or using artificial intelligence machine learning tools in terms of these subdisciplines of chemistry in 2020. When you actually look at the difference in publications, patents, or various abstracts, in particular to the ACS National Abstract, you clearly see that the rise in the publications is beyond 2017, either be it the publications, literature publications, or journal publications, or even the patent abstracts there. Now, when you look at this in depth, and when you try to look at which subject areas have been studied in depth in terms of artificial intelligence research areas, you see again the analytical chemistry has the topmost publication records, and there is a very small subset of organic chemistry, pharmacology, natural product synthesis, polymer, where the research in terms of artificial intelligence is picking up either in the space of journal publications or in the space of patent publications. When you dig a little bit deeper into it, you really find that the basis of all those publications are either small molecules in terms of journal publications or the nucleic acid sequences and small molecules when it comes to patent publications. So what I learned from this is that when we try to apply artificial intelligence or machine learnings into chemical sciences, we all think about having the research allocated to the small molecules or the chemistry structures. So you all need to think about chemistry structures. When you try to understand a little bit deeper or a little bit broader also in terms of various subject areas, what artificial intelligence and machine learning has touched base upon in terms of chemical sciences or pharma sciences, you clearly see that there is a lot of ongoing activities in terms of finding or predicting reaction outcomes, finding or predicting molecular property predictions, in terms of nanotechnology, wastewater management, designing of molecules, and drug discovery. We all know, and people who have experienced the drug discovery research all know how useful the CAD technology is, computer-aided drug designing. But at the same time, we also know that the technology cannot substitute our thought processes in predicting the molecules where we want to progress them as a drug molecules. And the recent developments is happening a lot in terms of retrosynthesis. It is one of the important tools when you want to synthesize a molecule, be it a materials, be it a chemical structure, or be it any field of chemistry. You need compounds to actually process them for the desired applications in terms of your respective researches. And for that, you need to make those molecules. And we all need to learn and understand about retrosynthesis, how one can design the synthesis route to achieve those. So I will touch base upon retrosynthesis as an example of artificial intelligence and machine learning in today's webinar. Before I go a little bit ahead into how one can develop that artificial intelligence powered by for the retrosynthesis, I just want to touch base upon what Reaxys at Elsevier Life Sciences has to offer. One actually can use the tool as Reaxys from starting of conceptualizing the research proposals to the end of publications, end-to-end delivery. If people working in the space of pharmaceutical sciences, they also can utilize the information coming out of Reaxys in terms of developing from hit to lead optimization, utilizing the pharmacological profiling data, the physical properties data, or the medicinal chemistry property data available within Reaxys as well. But as I said, today's webinar is more about the retrosynthesis as one of the application tools within those artificial intelligence and machine learning space. So we will concentrate on the synthesis planning part of the overall process, because every chemist need to make and synthesize molecules there. When it comes to molecules and be a medium complex to a more complex natural product molecules, everybody starts thinking in a way that how I can make it. What we look into is the literatures. We like to do a lot of literatures on how individual steps of those molecules can be made. We then decide what to make, how efficiently to make it, the compound. This process actually was started of predicting or requesting computers to predict those based on the formulas or based on those algorithms by the Nobel laureate Professor E.J. Corey way back in 1968. But when E.J. Corey started this predictive model, he started writing those algorithms or those rules, retro rules, in terms of manual hand-coded rules. He has to write every rule and then feed it up in the computers and help the request the computers to predict better. But with the explosion of chemistry from 1968 to now, recently 2023, you see a huge exponential expansion of chemistry as well as the various reaction steps. And to predict those, one needs to integrate artificial intelligence, machine learning techniques to have those hand-encoded rules into automated encoded rules there. And I will talk more about those encoded rules. When one wants to come up with a synthesis of a particular given molecule, he can have an overall prediction as a retrosynthesis one-step solutions there. So he or she or the researcher will get a complete synthesis route predicted by the computer there. Or one can apply those forward reaction predictions there, a step-by-step prediction approaches where one can design or understand individual reactivity and reaction conditions of a particular given step in this overall synthetic procedures. Or, as I said, one can look at the various databases and run those databases searches for individual step conversions to come up with a particular synthesis route for a given molecule or a desired molecule of your interest there. So it's like playing a game of chess. You want to try it out that should I go this step, should I apply one step or the other step so that I have the lesser number of routes and also I do it better in terms of time and efficiency there. So now when you compare a particular molecule and you want to disconnect that, there are multiple ways of disconnecting a given molecule there based on our experiences, based on our learning, based on the research group we are into it. Because every research group has their own methodologies and they want to deploy or employ their own methodologies into the retrosynthesis processes. So once you start disconnecting a molecule, either you can go multi ways in terms of the breadth of those disconnections or the depth of the disconnections. And when you want to compare these disconnections with, say, game of chess or the game of AlphaGo, if you compare this, you see that the retrosynthesis has a lot of options in terms of the breadth of the synthesis, and it can cross greater than 1 million options in terms of the breadth. But when you talk about the depth of the synthesis, in average, in the literature, we found that there are almost 12 to 15 average number of steps. And when it compares to these games, there are a lot many lesser steps in terms of the depth. So you need to have specific defined rules to help computers predict the retrosynthesis pathways for a design given molecules. One needs to also have the best possible rules to have the better predictions. One also needs to have the effective algorithms in place to have those better predictions when it comes to the predictive retrosynthesis. So what you need, as I said, is the data. And when the data is there, it can be coming out of any database. So for example, I have taken here the Reaxys database as it is the hallmark of the Elsevier Life Sciences developmental tool in terms of helping chemical sciences. So you either retrieve the data in terms of API files or the flat files or other sources, then use those data sets to transform the data, store it, clean it, and then combine it to desired algorithms, uncover those patterns in terms of analysis. Now, these are the two steps. The transform analysis steps are the most painstaking and important steps in the overall process of development of any predictive tools. And in terms of retrosynthesis, you need to assign the roles. You need to remove those duplications there. Then you need to do the atom mapping in overall process, apply format conversions, class creations, fingerprints, and then rule extractions. So once you do that, one can then develop those model, train those model, validate those model, again with the repetitive iterations, what I've talked about in a couple of slides before when I was talking about machine learning. And once you have those models in place, then one can deploy those predictive models and then scale up based on the requirement there. So when you talk about rule extraction, what does it mean and how computers can actually extract rules? So to understand and extract rules better, we need to feed the chemical structures into computer in the right format there. And for that, we need to understand how we can transform a literature reference article into and feed that into the reaction databases of computer to have better predictions there. And to do that, most people have been using canonicalized connection tables to convert the structural image to the software in terms of molecules, reactions, reagents, or reaction conditions there. So when you talk about a reaction, we need to have a right representation of those reaction files in terms of the RxN, RDF, or CML files. And to convert the structures, we can employ or deploy the SMILES notations or the Inchiki notations to feed that into the computers there. So when you talk about a particular reaction in terms in here, we talk about acetate formation. What we need to understand is the graph of that reactions there. One needs to do the right atom mapping. So you number those atoms and map those atoms. One needs to understand which are those conventional single double aromatic bond, which can then turn into those dynamic bond where we can do the break make bond and understand how a reactions center is being generated there to predict those reactions in a better way. To make it simple, when you talk about a public reaction and the representation here is to make that amide formation, you have the amine in place, you have the acid in place. You then do the SMILES standardization, convert them into those SMILES notations, do those reaction deduplications. So whatever the reactions reported in the literature in terms of amide formations, combining amine to the acid to make the amide, you deduplicate that, remove those non-participating groups, the reagents, the solvents, the catalysts there, and then do the atom mapping there. So once you do those atom mapping, from that atom mapping, a template is extracted. And this is what a rule is. So there may be thousands of amide formation reactions available in literature there. So a reaction which is repeated or reported at least 4 times in literature, from that you can easily extract or take it as a rule. So amine react with the acid group, the COOH, to form the COOH group. This becomes a rule. So like that, when you apply that to a particular molecule, and I have taken an example of a Pfizer molecule which was developed as an oral molecule to treat COVID-19 here, and then deploy those disconnection approaches. You can apply various rules of disconnection at either Rx, Ry, Rz, or Rw point, and then come up with those disconnections there and apply those synthons, and further apply those in-scope filter to those synthons to now predict those starting materials which are commercially available there. So the steps will be more iterative when you talk about those retro disconnections, applying those rules and in-scope filters there. Once you do that, you end up in commercially available starting materials to have those predicted steps to synthesize a given molecule there. We were really fortunate to have Professor Waller as our collaborator. He was the game changer in terms of the AI-driven synthesis, applying the 3 layers of neural network and Monte Carlo tree search to predict synthesis of either known molecules or the newly designed synthetic structures. This helped us to transform those rules in automated way. So reaccess retrosynthesis, which was developed in collaboration with Professor Waller, we can actually include those newer reactions coming up every now and then in the literature space and convert those into rules and help those model develop and predict better routes with the application of newer synthetic procedures or newer reactions available in the literatures. We have been doing this from 2015 to 2021 December update, and we do these procedures of extracting the rule and adding to those newer reactions to have better predictions in the reaxis retrosynthesis space. We were been awarded the best chemistry predictive analytics specialist award in 2020 after this designing of this retrosynthesis tool. In a nutshell, you can enter a particular molecule in the drawing space there, and then it provides route, and for every given steps, it provides you 25 different synthetic conversions or the organic transformations of functional group transformation options when you go step by step there. You can delete, add it, all those steps, and I will show you based on the time available a small demo of this as well at the end of my talk. As I said earlier, we didn't stop it there. We wanted to utilize these options and see that feedback coming out of those experienced chemists or medicinal chemists. And we turn around to Professor Carrera, who is again editor of Journal of Chemical Society, Professor Regis, who was president of European Chemical Society in 2021. And also in India, we are collaborating with Professor Ram Shastri, who is at IISER Mohali there. What we have done in terms of collaboration, I am just providing you an example of that, of collaboration with Professor Carrera here. We chose around 30 complex molecules, and you can have those representation of molecules seen here in the picture here. There were seven teams at the end of Professor Carrera's Carrera there, which consisted of PhDs and postdocs there, and each team were consisting of 3 to 4 researchers. At least there was one junior and one senior in each team. They utilized their own learnings to come up with synthesis of those 30 odd molecules here. And that was also compared with the predicted synthesis routes coming out of this retrosynthesis tool there. And the feedback from the Carrera group was interesting approaches and robust route were proposed by these retrosynthesis tools. The tool is quite user-friendly and intuitive in nature. And if you are used to reaxis tool, it is very easy to use this tool in a longer run. The tool also helps you to save time, and obviously when you save time, and you will automatically save the cost also, and you will actually produce literature or submit those articles faster, particularly towards designing synthetic routes. And when you apply this to medicinal chemistry, where you need to design newer molecules which can be patentable, this tool is even better helpful there. They also had a comment that it is not a black box AI, as it shows literature precedences, an example which underpins the predicted routes. And that is the confidence we had when we then shifted this overall collaboration from Professor Carrera to Professor Regis, who also has their own companies, and now they have been applying this tool in their day-to-day use. And now we are in India, we are running this collaboration with Professor Ram Shastri here as well. The overall takeaways were that the the predictive retrosynthesis tool is user-friendly in nature. It provides robust predictions of drug-like molecules where chemists need to do the review of predicted routes and make those necessary adjustments to the routes by utilizing their own intelligence and own learning into it, so that it helps them to solve those problems faster rather than trying a lot of reactions to come up to perform those experiments in the lab. Due to this, it saves a lot of time for designing routes and also trying out newer reactions. It saves a lot of money as well, because you do not have to buy so many reagents to execute those experiments in the lab. The steps are quite innovative, which have been predicted by the synthetic route, and one can easily go and write a publication out of it. The challenge is what we have right now is that the highly complex natural products are difficult to predict in this predictive retrosynthesis route based on those disconnections of the steps right now. So in a nutshell, you need the chemist knowledge combining with this predictive retrosynthesis, which is a power combination. And as I said, that I will give my statement that you cannot replace a chemist, and that's what the talk was with the question that can we replace the chemist with AI? It cannot replace, but it certainly augments and supports the work. The human and machine interaction certainly is a powerful combination, which, if taken help, can actually solve complex problems. And hence, the statement that the AI cannot replace chemists, as per my interference and my perception, based on the today's talk. Now, what to expect when I talk about reactive predictive retrosynthesis? There is break and make protect bond ready for release available in the predictive retrosynthesis module. There, we are also coming up with the model update and customized models when you talk about the model related updates. When you talk about user interface related updates coming up in the predictive retrosynthesis module, we have reactive commercial substances and derivatives as a new building block libraries will be available in the tool there. The alignment of the reactants and highlighting is ready for release, and one can expect that in a month's time. Reactive reaction examples and selection of the export is also ready to release. Right now, one can export and directly copy those results in CDX file, in the ChemDraw file, and export them as a PDF. One can also now expect to import multiple structures at a time. So we are ready to release those batch import available in the predictive synthesis module there. And acknowledgement to Professor Carrera, who is at ATX Zurich. His experienced chemists there, Maurice Claassen and Maurice Hansen. Professor Floris Regis at Radboud University and his subordinate Daniel Blanco, Florian Zelke and Manix, and Professor Ram Shastri and his PhD students at IISER Mohali there. So it's all been collaborative work at with Reaxys team and his distinguished scientists at the respective institute to come up and make this proof of concept in terms of the predictive retrosynthesis model there. We also have been working not with just the academician, but with the industry as well, partners. So we have taken their considerations, their suggestions into account while developing this predictive retrosynthesis tool. Janssen, AstraZeneca, Amgen, Pfizer are few here which are captured, to name a few, which have been providing the updates in terms of developmental strategies in reactive predictive retrosynthesis, and also now they are the proud users of predictive retrosynthesis module in their research activities. So what you should remember at the end of this talk, you should remember that this tool has been developed using 15 million single-step reactions, from which the auto-extracted rules, the 4 lakh rules, have been deployed. And that's what I have explained you about how a rule can be extracted out of a reaction there. Once you have extracted the rules, we have deployed the 3 layers of neural network and Monte Carlo research in terms of the AI/ML technologies to deliver you the best-in-class predictive retrosynthesis tool. If you have questions on this, before I shift to the demo, you can write it down, the contact person's name, if you want to talk to in Southeast Asia region or Australia, New Zealand region, you can reach out to Raymond. And for South Asia, including India, Pakistan, Sri Lanka, Bangladesh, you can reach out to Ravindra Gupta for any further questions, or if you want to experience the tool. You also can reach out to me anytime. I have my contact details here. You can reach out to me anytime if you have further questions. And before I take any questions, I will just like to show you a small demo of those retrosynthesis tool, what we have developed in Reaxys. I'll reshare the screen here. So this is the retrosynthesis module available within Reaxys there. We have a tab there. One can actually save all their different projects, which I have also run. You can see here. There you can copy paste. If you want to draw a structure, you can copy paste or type a name of a compound and have those structure drawn here directly for you. You can paste your smiles notations and have those structure paste when you want to draw those molecules for predicting routes. One can actually use various features and functions or the properties available for the users. One can choose the diversity of routes in terms of the reaction steps or the building blocks there. And again, I'm not going into detail. I leave it up to you to further reach out to those individuals, Ravindra and Raymond there. But I'm just showing you a flavor or providing you the flavor of what is available in terms of the properties or adjustments in terms of the functions when you want to actually design synthetic routes via this module. I'll just take you through the recent molecule available in the Drug Hunter website, the difamilast, or even I have run the molecule, the camlipixant as well. So if you see here, because this is known molecule, you can either procure it here, you have this published route, and also you can compare this with the predicted route. So you see here the published routes in the step, the convergence, divergence, route topology is available here, and also the predicted routes directly available here. So if you click on this view, you will see the complete synthetic predictions of those routes here. At the same time, you can actually compare by going and hitting those tabs above this. The blue square is for the published routes and the green square is for the predicted route. So you can directly compare the synthesis here. For every given step, as I said, you have this 25 examples in the literature for those functional group transformation, which you can either click it here and show reaction conditions. So it will directly show those reaction conditions here, or can hover around these steps here. One can, if one finds that this starting material or the building block is costly for them. So if you click on or hover this mouse icon, you will see that this is highly costly. So one can go a step backwards and modify the synthetic route into a customized synthetic route by adding a step backwards there and to augment or direct it to a cheaper starting material there. So if you can hover always here, and you see here the starting materials are already captured here. So one can add that as a backward step, and you will see a customized synthetic route icon in terms of yellow in the about tab as well. So this helps those users to modify the synthetic procedures based on their need. They can add a step or delete the step any time they want it. They can export the synthetic route in terms of multiple formats here. If you are working in eLab notebook, particularly the pharma companies do use it, they can actually add this route directly into those ELN pages and put a date stamp over it for the patentability there. One can directly copy paste the synthetic route into the ChemDraw file here, and I will just show you the ChemOffice file. You can directly paste into the ChemDraw by this copy feature directly here. So this is in a nutshell the overall module here, but I leave it up to the individuals to reach out to those individuals, Ravindra and Raymond, if you want to know more about it. And I'm happy to take questions. I'm seeing there are 4 questions in here. So Mr. Vajrak is asking, is this presentation recorded? It is recorded, and you will be getting the recording once you provide those feedback form. There is another question. Is there any examples of analytical chemistry, especially in testing? So yes, there are examples. I will, if you reach out to me directly, I will be able to provide you those literature references there. But as that was not in the scope of my presentation today, I have not captured that in there. Is this tool an open source? This is a question by Mr. Vishwanath. This is not open source there. You need to subscribe to Reaxis predictive retrosynthesis in order to use it. This will guide us only for possible synthons or reagents and solvent as well. This is a question from Dr. Arote. So yes, this will guide you to possible synthons and reagents with the relative example or respective examples of the functional group transformations available for those individual steps in those predictive retrosynthesis route. Vivek Yadav is asking, can we select a reagent for better yield from AI? Right now, that option to select a reagent for better yield is not available, but at the same time, what I have demonstrated is that it provides you those 25 examples per reaction step, and as a knowledge user of this chemistry, you will be able to understand which particular experimental procedure is best suited to achieve those higher yield or better yield in terms of synthesis there. Ms. Neha is asking that this also reduce steps of existing synthesis. Yes, it certainly reduce steps of existing synthesis. You also can, as I showed you, you can compare the steps in the published synthetic route versus those predictive and decide which is the best for you to execute those experiments in the lab. Sir, is this only for organic molecules? Yes, at this moment, this is only for organic molecules. We are coming up with predictions of inorganic molecules as well. The scope is not wide enough for inorganic molecules at this moment, but you can certainly try it out or provide me those miles notation of those molecules if you want to test it for your non-organic molecule space, and we will be able to provide you those results of your desired molecules. Ms. Alka is asking, sir, it make a new route for already synthesized molecule? Yes, as I demonstrated, you have a new route for a known molecule, which one can easily execute those experimental lab and have a publications right away there. What are the compounds which cannot be retrosynthesized well by reaxis? Example, natural products or anything related. Has been asked by an anonymous attendee. Yes, highly complex natural products are the one which are difficult to predict based on those retrosynthesis tool. But we also have, I will just show you a step-by-step procedure. So when you actually want, say, the molecule, take this example here, or I will just go to the synthesis project and show you can go step by step backwards. When you have a complex natural product system as your desired molecules there. So if you see here on the various options here, you have this last step options only. So if you select this, the rule will tell you the penultimate step predictions, and you can go a step by step backwards in order to resolve the issues with the complex natural products. How reaxis is calculating synthetic score for the product? So based on the literature, you captured it right. So if you go to my various possible synthesis route, let me open that option. The reaxis based on the literature examples and the related respective literatures examples for individual step within those retrosynthesis options, it helps you predict those or it helps you provide those scores in analyzing those molecules there. So if you see here, the scores are available for those predictions here. Let me go to the synthesis route. And whatever the parameters you have chosen can also be seen for every molecule of your interest, which you have been capturing under your space there. So that is also a possibility there. Can we predict chiral resolution reagents? No, Partha, we cannot predict chirality. But as a chemist, you all know how to introduce a chirality. Either you start with the commercially available enantiomerically pure starting material, or use those chiral reagents to introduce those chirality or enantiolicity or diastolicity in a molecule there. And hence you will be able to come up with those resolutions when it is a chiral molecule of interest. Is there in trial version that can be accessed? Yes, you again reach out to Ravindra or Raymond there, and they will be able to help you in these regards. How this tool and AI manage the incorrect data? There are some reactions described in literature to be proved wrong. how to reduce the use of this wrong data? This is a very good question. We have been, as I said, and as I showed you, we have been collaborating with industry partners, and we also are trying to get the information on the negative reaction data, which we are using that to to help us predict reactions better in terms of the execution experimentally. So the negative reaction data is one which is in development and which also has been provided by those industry partners, again based on the intellectual property rights and the legalities there. So yes, to answer you in short, reaction retrosynthesis helps you to reduce those incorrect reaction predictions as well. Is there, this is also valid for polymer? So Mr. Sagar Patil, this is not valid for complex polymers again, but reactions do have procedures and available data for polymers as well. Can we eliminate side reactions or byproduct formations? Again, good question from Ms. Vaishali. We also are developing, so in newer developments or the future developments, upcoming developments, you will find the options to say remove a particular reagent which is either toxic or can cause explosions there. So say you want to avoid acid reactions in your scale-up procedures. So those kind of options will be upcoming in and are in the development right now. And you will see those available options in reaction retrosynthesis module in future as well. Can we paste the molecule structure from ChemDraw or any other tools? Yes, we can copy paste the molecules directly, either the structures. So good point here. The drawing tool also has ChemDraw here. If you see here, the ChemDraw option is available. So already drawn structure can be copy pasted directly into Reaxys modules here. Can this app predict amount? No, it cannot. The prediction of amount, if you are a user of SciFinder, they show you that you can achieve this yield or that yield, but it is very irrespective or it is non-judgmental in terms of yield. Actually, one cannot predict the yield of a reactions in a right way. Also, if two persons are performing a similar reactions, both the persons can achieve different yields of based on the way they actually work out those reactions as well. So predictions of the yields are not the right way, and hence we do not provide them. Can we use the tool to predict the best way to separate polymer blends? No, at this moment, but the information, Mr. Dattatreya, is available in Reaxys. So you can utilize Reaxys information to separate those polymer blend based on the information available in the literature. So I think I have this will guide us only for possible. Yes, I have answered all those questions available, but I am open to your questions if you want to ask more. And I leave it up to my co-host or panelist, Mr. Ravindra or Adeline, if they have anything or if I have missed out anything, to let me know, and I will be happy to answer this. I again request you to provide your feedback and also reach out to those individuals. I will again show them before ending this webinar. Sir, how it is different from SciFinder? So SciFinder can go only 4 steps backwards in the predictive retrosynthesis way. It most of the time ends up in non-commercially available starting material when you actually look out for predictions of medium complexity to the complex molecule. Whereas Reaxys predictive retrosynthesis is designed a way for you to have the starting materials available which you can procure commercially. So it will always provide you the options in terms of procuring those reagents, building blocks commercially. And this is the basic difference between Reaxys and SciFinder. I will not able to demonstrate it more deeper here based on the time available now. But yes, you again can reach out to Ravindra or Raymond to have a separate session at your end to understand it better. Reaction condition optimization. Is there any way to narrow down the best conditions, temperature, catalyst, etc. for a reaction? Yes, we have that option in Reaxys directly there to search particular reactions with highest or best possible yields. I will urge you to look out for our third webinar in this webinar series, wherein we are going to have an expert professor as a speaker alongside me, who will demonstrate on using Reaxys efficiently and productively for either education or teaching, and also in research. So you look out for that webinar. I request Adeline or Raymond or Ravindra to post that link in the chat of our web page, so that user can directly go and register for those webinars. I think I have done with my Q&A sessions. I have answered almost all. Ravindra has posted me, what is the accuracy of AI in giving the latest updates on medicinal chemistry? In terms of medicinal chemistry, right now we are developing the predictive tool in terms of properties such as C-log-P, such as CYP inhibition, such as blood-brain barrier penetration, such as cellular permeability in terms of PAMPA or CACO2. All these predictions are in developmental stage, very preliminary developmental stage. But yes, there are tools available. People are working on it in terms of predicting these properties for designing better molecules when it comes to medicinal chemistry space. How can we implement AI in plant-based extract product to validate the method, as it is complex matrix? So again, right now I have not touched based or read any article in terms of extracting products from plant with the help of AI. But again, coming back to Reaxys, when you are talking about natural products and extractions, we do have we do provide information on what molecules have been reported in literature in terms of possible extracted from a particular plant species or animal species or aquatic species as well. So again, I request you to reach out to those individuals to understand how to utilize the overall Reaxys tool and embed it into your either education workflows or research workflows. I think I'm done with answering all those questions here. I request you to again provide, you will receive a feedback link here, and I request you to provide your feedback, and please reach out to those individuals if you want to know more. Adeline has already posted in the chat box the link to the upcoming webinars. So I request you, if you find this helpful, to register for those upcoming webinars. One will be in the tentatively in first week of August, which will be in terms of utilizing Reaxys information for designing compounds, also progressing your compounds from hit identification to lead identification to the toxicity stage. I will be demonstrating how you can utilize this tool for drug discovery and drug repurposing as well in my second webinar. And the third webinar, as I said, will be the webinar to look out for if you are looking to improve your productivity and efficiency in terms of reactions or education and teaching. As this webinar will be held in collaboration with Professor Clegg, who is a distinguished professor at Queensland University. So please look out for these webinars, register for this, and reach out to those individuals. I will reshare the contact people list here, so you can reach out to either me or Raymond. Sorry, I will share the screen again. Raymond or Ravindra. So please
Mandar,
reach
I've
out.
also posted in the chat, Mandar.
Yeah, perfect. But I'm again showing them so that they can reach out. So we are at the end of the webinar, and if you have any further questions, I will be happy to answer them. As this been but otherwise, feel free to reach out to us again, and we'll be happy to take you in those future discussions in terms of using reaxis or predictive retrosynthesis for your research or education purposes. Handling, if there are no more questions, we can then close the webinar, right?
Yes. Thank you so much, Mandar, for a very informative session. I think that we managed to get a lot of questions here, and I'm sure there'll be more coming your way or through Raymond or Ravindra. And I would like to thank everyone who made the effort and time to attend this session. Please do register for the following sessions. There's more to come, and we look forward to seeing you again in our next few webinars. Have a good day, and we'll see you soon.
Yeah, feedback will be shared after the webinar. So yes, we will receive that.
Yes, thank you.
Perfect. See you all. Have a great day, all of you. Bye.